For years, James Webb has felt like the final word in space telescopes, a mirror the size of a tennis court, staring billions of years into the past, giving humanity the sense that we'd finally built the ultimate eye in space. But in just over 6 weeks, on August 30th, 2026, NASA is launching something that doesn't try to beat Webb at its own game at all. It's built to do something Webb was never designed to do, to move so wide, so fast, and across so much of the sky at once that it can measure the actual shape of the invisible universe, the roughly 95% of everything that exists that we still cannot see, touch, or fully explain. This is the Nancy Grace Roman Space Telescope, and it's not a smaller, cheaper Webb. It's an entirely different kind of instrument, and what it's built to reveal is stranger and more consequential than most people currently realize. Stay with me, because in just 6 weeks, astronomy may stop asking what one galaxy looks like and start asking what billions of them are doing all at once. And let's start with the numbers, because on paper, Roman doesn't look like an obvious successor to anything. Its primary mirror measures 2.4 meters across, the same class as Hubble and considerably smaller than Webb's 6.5 meter mirror. If you judge telescopes purely by mirror size, that looks like a step backward. That's exactly the trap, because Roman's real power was never about depth, it's about scale. This observatory carries a field of view roughly 100 times larger than Webb's, meaning a single Roman image can cover an area of sky that would take Webb around 100 separate pointings to photograph in the same detail. Webb is a microscope. Roman is a wide-angle cosmic survey machine, capable of capturing images as sharp as Hubble's across a field of view 100 times larger in one single exposure. Here's why that distinction actually matters more than raw mirror size. The biggest open questions in cosmology right now, the nature of dark matter and dark energy, can't be solved by staring intensely at one object at a time. They require massive statistical power, enormous samples, real breadth. Roman was engineered specifically to deliver exactly that. Everything humanity has ever touched, measured, or built out of ordinary matter accounts for only about 5% of the total universe. The other 95% is dark matter and dark energy, invisible components that dominate reality while remaining among the biggest unsolved problems in modern physics. Dark matter reveals itself because galaxies rotate too fast to be held together by the visible matter we can actually see. The stars at the outer edges should fly apart entirely, but they don't, which means something unseen is providing extra gravitational pull. Dark energy is stranger still, an invisible force that appears to be driving the universe's expansion to accelerate over cosmic time, pushing space itself apart faster and faster the longer you watch it. We know these effects are real because we can measure their consequences. What they actually are remains genuinely unresolved. That's exactly where Roman becomes scientifically significant. It was engineered specifically to measure those invisible forces directly through their effect on light and cosmic structure, rather than simply inferring their presence indirectly the way earlier surveys have had to. Its construction was completed on November 25, 2025, at NASA's Goddard Space Flight Center in Maryland, following a punishing series of environmental tests blasted with the actual sound intensity of a rocket launch, violently shaken inside a protective clean tent, and cooled inside a thermal vacuum chamber down to the same extreme. Temperatures it will face in deep space. On June 21, 2026, the nearly 8,200 kilogram observatory, about 18,000 pounds, arrived at Kennedy Space Center in Florida via NASA's Pegasus barge. And as of early July, technicians have already rotated it to vertical and begun powered system checkouts confirming it survived the journey intact. NASA is now targeting no earlier than August 30th for liftoff aboard a SpaceX Falcon Heavy rocket, roughly 9 months ahead of the mission's official required readiness date of May 2027, a genuinely rare occurrence for a NASA flagship mission of this scale and cost. Let's break down exactly how Roman plans to pull off something this ambitious, because the actual science behind it is genuinely elegant. Roman's greatest tool is a phenomenon called gravitational lensing, a direct consequence of Einstein's general relativity. Mass bends space-time, and light bends along with it. So even though dark matter itself is completely invisible, its gravity still warps the light coming from galaxies positioned behind it, from our point of view. Those background galaxies end up looking subtly stretched, distorted, or correlated in shape in ways they simply shouldn't if no hidden mass were sitting between them and us. Now, do that kind of measurement with a small sample of galaxies, and you get hints, suggestive but inconclusive. Do it with an enormous sample, and you get an actual map. Roman is designed to do it with roughly 2 billion galaxies. That number is the entire leap. Previous large-scale surveys attempting this kind of measurement have typically worked with tens of millions of galaxies. Roman moves into a completely different regime, one where the dark matter signal stops being a subtle statistical whisper and starts becoming an unmistakable, overwhelming pattern. The mission is expected to produce the first truly enormous three-dimensional maps of dark matter distribution across genuinely cosmological volumes of space. Not just a two-dimensional projection, but real depth, real structure, mapped out across billions of light years. And while collecting that data, Roman will simultaneously measure the expansion history of the universe across roughly the past 10 billion years, using both distant supernova and the large-scale patterns formed by galaxy clustering. That means Roman isn't just hunting for where dark matter sits in the cosmos. It's also directly testing whether dark energy behaves the way Einstein's original cosmological constant predicted. A simple, unchanging force, or whether it's doing something more exotic, and evolving over cosmic time, a distinction that could point toward genuinely new physics we haven't discovered yet. As ambitious as that dark universe survey is, it's only one half of Roman's core mission, and the second half is just as significant. At the same time it's mapping dark matter and dark energy, Roman will be continuously monitoring around 100 million stars in the crowded central bulge of our own Milky Way galaxy, watching specifically for microlensing events, brief, tiny brightenings that occur when a foreground object passes precisely between us and a background star, its gravity briefly acting like a natural magnifying lens. If that foreground object happens to have a planet orbiting it, that planet leaves its own smaller secondary signature layered on top of the main brightening event. This method matters enormously because it catches an entire category of planet that transit-based surveys like Kepler and TESS routinely miss, specifically colder, more distant worlds orbiting far from their host stars, the kind of planetary architecture that actually resembles the outer layout of our own solar system, with worlds like Jupiter, Saturn, Uranus, and Neptune sitting well beyond the reach of most exoplanet hunting techniques currently in use. Roman's science team expects the mission to discover thousands of these previously undetectable planets over its operational lifetime, filling in a genuinely significant blind spot in our current census of how planetary systems across the galaxy are actually built. And here's something worth sitting with, a pattern that's held true across every major space telescope NASA has ever launched. The single most important discoveries a telescope makes are frequently not the ones it was originally designed to find. Hubble proved that repeatedly, uncovering entire categories of cosmic phenomena nobody anticipated when it launched in 1990. James Webb has already done the same thing multiple times over, turning up unexpectedly massive early galaxies and mysterious compact objects that weren't part of its original science case. Roman is very likely to follow that same pattern, because once you start surveying the sky at this particular combination of scale, resolution, and repeated cadence, something unexpected is essentially guaranteed to show up. Strange, unclassified transient events, unusual gravitational lensing patterns nobody predicted, entirely new categories of cosmic objects that don't fit any existing label. Roman's official, funded mission is to measure the invisible universe. Its unofficial, and arguably more exciting, mission is to surprise the scientists who built it. Here's what actually happens to astronomy itself once an instrument starts operating at the numbers Roman is designed for. For most of scientific history, major discoveries have come from staring intensely at one target, one region, one specific puzzle at a time, patiently extracting every possible detail before moving on to the next object. Roman represents a genuinely different era of observation, one where the sky becomes a data field so enormous that hidden statistical patterns simply can't stay hidden anymore, not because they weren't real before, but because no previous telescope had enough combined coverage and repeated observation to actually notice them. Consider what that shift in scale actually means in practice. 2 billion galaxies surveyed for the dark energy and dark matter mapping campaign. 100 million stars monitored continuously for the exoplanet microlensing survey. A combined cadence and total sky coverage that no previous space telescope has ever brought, together in a single mission. When an observatory starts operating at that volume, the universe stops behaving like a collection of isolated, individually interesting objects and starts behaving like something you can actually study statistically, as a measurable system with real, testable structure. Roman isn't just going to show astronomers more of the universe. It's going to reveal whether the cosmos has been following statistical patterns all along that we simply lacked the observational coverage to detect before now. That's exactly why this mission carries so much scientific weight, in the best possible sense. Moving from small, brilliant individual case studies to genuine planet-scale and galaxy-scale census, science removes a lot of the wiggle room that's historically let competing theories coexist without being fully tested. Either dark matter's gravitational fingerprints show up cleanly and consistently across a genuinely cosmic scale, or something about our current theoretical framework needs serious revision. Either dark energy behaves consistently as a simple, constant force across the roughly 10 billion years of cosmic history Roman will be able to measure, or we're looking at a deeper, currently hidden problem in fundamental physics. Roman isn't just broadening the field of view available to astronomers, it's tightening the pressure on the universe itself to actually explain what it's doing, rather than allowing multiple competing models to remain equally plausible simply due to a lack of sufficient data. One of the more common misconceptions circulating about this mission is that Roman and James Webb are somehow competing observatories, rivals for funding, attention, or scientific relevance. They're not. They're better understood as two complementary halves of a genuinely more powerful combined system. Webb is the close-up specialist, capable of staring deep into a single object and extracting an almost unbelievable level of detail. Roman is the cosmic scout, sweeping enormous regions of the sky to identify exactly where the most scientifically interesting activity is actually happening. One instrument finds the broader patterns. The other leans in close enough to actually read them. That partnership genuinely changes how future astronomical research will get done. Roman is expected to identify unusual gravitational lensing events, unexpected supernovae as they happen, strange galaxy structures that don't fit, standard classification, promising exoplanet signals, and specific regions of sky where dark matter appears to be shaping visible structure in especially revealing ways. Once Roman flags those targets, Webb can then turn its considerably larger, more sensitive mirror directly toward those specific coordinates and study them with a level of spectroscopic and imaging detail that Roman, built for breadth rather than depth, was simply never designed to provide on its own. Roman finds where the universe appears to be hiding its most important secrets. Webb gets close enough to actually read them. That division of labor is arguably the deepest reason this mission matters as much as it does. Roman isn't simply another telescope joining an already accomplished fleet of NASA observatories. It's the missing wide-field engine that makes the rest of that fleet meaningfully more capable, giving astronomers, for what may be the first time in the field's history, the ability to understand both the overall forest and the individual trees within the same coordinated observational strategy, rather than being forced to choose between broad coverage and fine detail. So let's bring this all together, because 6 weeks from today, assuming NASA's current schedule holds, a Falcon Heavy rocket is going to lift off from Launch Complex 39A at Kennedy Space Center, carrying a telescope that could genuinely change how humanity understands the largest and smallest scales of reality at the same time, not by outcompeting James Webb, by doing something Webb was never built to attempt. Let's connect every piece of this story one final time, because the full picture is more compelling than any single fact on its own. Roman finished construction on November 25, 2025, survived a punishing series of launch, simulation, and thermal vacuum tests, and arrived at Kennedy Space Center on June 21, 2026, already standing vertical and undergoing powered checkouts as of early July, currently targeting an August 30th launch, nearly 9 months ahead of its official required deadline. Once it reaches its permanent operating position at the second Sun-Earth Lagrange point, roughly 1 million miles from Earth, the exact same stable gravitational neighborhood James Webb already calls home, Roman will begin a primary mission designed to last 5 years, though NASA's own engineers expect its propellant reserves to realistically lasting twice that long, meaning this observatory could still be producing new discoveries well into the late 2030s. During that time, its wide-field instrument, a 300.8 megapixel camera capturing images as sharp as Hubble's across a field of view, roughly 100 times larger, will survey approximately 2 billion galaxies to build the first genuinely three-dimensional maps of dark matter. Distribution across cosmological distances, while simultaneously tracking the universe's expansion history across roughly the last 10 billion years to determine whether dark energy behaves as a simple constant force or something considerably stranger. At the same time, that same instrument will continuously monitor around 100 million stars in our galaxy's crowded central bulge, hunting for the subtle gravitational microlensing signatures of distant exoplanets, expected to reveal thousands of cold, distant worlds that current transit-based surveys like Kepler and TESS simply cannot detect. And its second instrument, the coronagraph, will demonstrate exactly the kind of precision starlight blocking technology that NASA's next planned flagship mission, the Habitable Worlds Observatory, will eventually depend on to directly image Earth-like planets orbiting other sun-like stars, a mission still in its early planning stages, but one that Roman's coronagraph work is directly paving the way for. None of this requires speculation or exaggeration to feel genuinely significant, because the scale alone does the work. 2 billion galaxies is a large enough sample that dark matter's gravitational signature, if our current models are even approximately correct, should show up as an unmistakable, overwhelming statistical pattern, rather than the subtle, easily disputed hints earlier smaller surveys have had to work with. And if that clean signal doesn't show up the way current theory predicts, that itself becomes one of the most important results in modern cosmology. A genuine crack in a framework physicists have relied on for decades. Either outcome, confirmation, or contradiction moves the field forward in a way that staring at individual objects one at a time simply cannot achieve. And this is really the heart of why Roman deserves your attention over the next several years, not just in the 6 weeks leading up to launch. James Webb already proved what an extraordinary single object can look like when you stare at it with enough patience and sensitivity. Roman is about to show us what billions of those objects are actually doing, all at once, across the full sweep of cosmic history, revealing whether the patterns astronomers have theorized about for decades genuinely hold up at the scale where they'd finally become undeniable. That shift from individual case studies to genuine planet and galaxy scale census science is exactly why this mission has the potential to reshape cosmology as significantly as any single telescope that's come before it. So here's what I want to leave you with. In just over 6 weeks, a machine designed specifically to map the invisible 95% of everything that exists is going to leave Earth. If its dark matter maps come back clean and consistent with our current models, that's one of the most important confirmations in the history of physics. If they don't, that's arguably even bigger, a genuine sign that our understanding of the universe has a real gap somewhere we haven't found yet. Which outcome do you think is more likely? Confirmation of what we already suspect, or a genuine surprise that sends cosmologists back to the drawing board? Tell me your prediction in the comments, because launch day is coming fast, and I'll be covering every milestone between now and Roman's arrival at L2. Subscribe and turn on notifications, because when this telescope opens its eyes for the first time, you're going to want to already be here to see what it finds.